All right, welcome back again to Physics Computer Science 219A. I'm glad you're here, especially because we have a fun topic to discuss today. We're going to talk about how a quantum computer can speed up exhaustive search for the solution to a problem. So we've discussed the last couple of lectures the black box setting, where we can talk about query complexity. And we saw that we can speed up period finding, for example, exponentially by allowing quantum queries relative to when we have only classical queries. And that algorithm is useful in practice because we can use it to compute efficiently the period of any function that we can compute efficiently. If we can compute the function, then we can determine its period, even if the period is exponentially long. And that was the key to the factoring algorithm. And there are other exponential speedups known. Exponential speedups are really cool because in the future, at least, it means that with quantum computers, we can expect to be able to solve problems which are hopelessly out of reach for the digital classical computers of the future. And I'm going to talk in the next lecture about another important exponential speedup, exponential as far as we know, which is using quantum computers to study quantum problems, likely to be an important application in the future. But today I'm going to talk about a speedup which is not exponential. It's in fact a quadratic speedup, meaning that the quantum time it takes to solve a problem goes like the square root of the classical time. Less spectacular than an exponential speedup for sure, but still interesting. And the one I'm going to talk about today, the speedup of exhaustive search, is in principle of quite broad applicability to many problems. It remains to be seen whether that quadratic speedup will be sufficient to make a practical difference at some time in the foreseeable future. Probably eventually it will. And it's an interesting thing to discuss, particularly because the argument is actually very simple and intuitive once you see what it is for understanding how this speed up in exhaustive search can be achieved quantumly. So what we might think about, or a way to justify what we're going to study, is we can imagine trying to solve an NP-hard combinatorial problem, like we're trying to find a satisfying instance for a formula or something like that. And there's no special structure to the problem that's obvious that we can exploit to solve the problem quickly. One way we could always solve it is just by doing an exhaustive search for the solution. If the problem's in NP, we have a verifier. Every time there's a trial solution, we can check to see whether that input is really accepted by the verifier or not. And we could run through all the possible solutions, but of course that would be an exponential time algorithm because there are an exponential number of candidate solutions that we'd have to try. In some cases, we really don't know a much better method than exhaustively searching for a solution. And to kind of formalize that so we can study it more deeply, we'll consider it in the black box setting, where there's a function which you can think of as sort of a model of a verifier, and there's just one possible n-bit string that it will accept out of 2 to the n possible strings. This function evaluates to 1 for one and only one string. Let's call that string W. Actually, I had a hard time deciding whether I was going to call it W or omega. And when I was making the slides, I called it W for a while, and then I switched over to omega, and I didn't fix that. But I'm going to call it W for now, and then later on, I may decide I prefer to call it omega. The W looks a lot like the omega. Anyway, hence the confusion. But what I mean here by f sub W of x is a function which rejects every input except for the string W. It gives 0 for any x not equal to W. For W, it gives 1. And that W is the solution to a problem that we'd like to find. we could find it by exhaustive search, but if they're all together capital N, let's say 2 to the little n, possible strings of length little n, binary strings of length little n, then we'll have to query an exponential number of times. Or if capital N is the total number of candidate solutions, I'd have to try at least half of them to have a probability of finding the solution successfully greater than 1/2. So I would need big omega of n queries in order to solve the problem. But quantumly, it turns out that just the square root of n queries are enough. That's the quadratic speed up. The way we achieve this miracle is called Grover's algorithm. And it's really pretty cool that we can search through n possible solutions in square root of n time with just square root of n queries. We do it by using quantum superposition, by querying in superposition. That's how we're able to surpass what we would be able to achieve classically. So first of all, we do what we've done in the past. We'll take our box, which computes the function. We can imagine it has an input and output register. There's some unitary that computes the function. And in order to be unitary, it preserves the input register. So it takes x, y to x, tensored with y XOR f sub w of x. In other words, if f evaluates to 1, it flips the value of y, and otherwise it doesn't do anything. Now, as we know, we can put the state minus 0 minus 1 divided by square root of 2 in that answer register, and the effect of that will be that what a query to this box does is it flips the phase of the state in a way that depends on the input x. Namely, it flips the phase if fw of x is equal to 1, and it doesn't do anything if fw of x is equal to 0. So we can forget about the answer register now because it's always going to be in the state minus, and just pay attention to the input register. So what a query does is of the capital N orthonormal basis states for our Hilbert space, it doesn't do anything to capital N minus 1 of them. And for the one marked string, that string that we're trying to find, namely x equals w, it changes the phase. It flips it to minus 1. So I can write this unitary this way as the identity minus twice the projection onto w. For anything orthogonal to w, it just acts like the identity. But for w, it becomes identity minus, well, 1 minus 2, minus 1, acting on the state w. So if there's any state that I query this box with, it can be written as a superposition of the orthonormal basis state w and some state orthogonal to w. Nothing happens to the part that's orthogonal to w. The part proportional to w changes phase. So you can think about that geometrically in the following way. If we imagine there's some direction in Hilbert space, which is picked out by the orthonormal basis state w, and then there's a hyperplane perpendicular to it, which contains all the vectors which are perpendicular to w, and the components that are perpendicular to w are unaffected. The component along w changes sign. So it's like a reflection of a vector. I tried to draw it here in that hyperplane. That's what a query does. So it takes this state. When we apply the query unitary use of w, it takes it to the other side of the hyperplane, reflects it by changing the sign of the coefficient of basis state w. Okay, so now I'm going to explain what the algorithm is, and we'll see how it works. The first thing we do is we prepare a state which is a uniform superposition of all possible basis states. One of those basis states is the one that we're looking for. A priori, we have no idea which one. So it makes sense to start out with a state which is a uniform superposition of them all, treats them all symmetrically, because we have no reason to favor one over another. Now, this is an easy state to make. We've made it before. We can make it with the quantum Fourier transform acting on the state 0, or if we're talking about n qubits, we can create it with a tensor product of n Hadamards, as you know. Now, whatever the marked string is, the corresponding basis state, I'll sometimes call that the marked state, has an inner product with this state, which I'm calling S, which I think I chose S because it stands for symmetric, treating all the basis states the same. The inner product is just going to be 1 over square root of n. The amplitude in this superposition for all strings is 1 over square root of n, including the marked string. Now, for reasons you'll see, I want to think of that as the sine of an angle. And n is a really big number. The angle is very small. I can use the linear approximation to the sine function. So the angle is very close to 1 over the square root of n. It's 1 over square root of n plus corrections, which are higher order in 1 over n. And now what our algorithm is going to consist of is many repeated applications of the same unitary, which I'm going to call U Grover, the Grover iteration because I'm going to do it many times. And it consists of a product of 2 unitaries, one of which is U sub W, that's the query to the box. And the other I'm going to call U sub S, and that's this unitary. It is 2 times projection onto S minus identity, okay? So what that does is for the orthonormal, for the state S, some vector in the Hilbert space, namely this one, it's just leaves the state alone. But for everything orthogonal to S, it flips its phase. So if you want to think about it geometrically, it reflects a vector in the axis defined by S. It doesn't change the component along S, and it flips all the other components. Now, this isn't so important for query complexity, but if I really wanted to use this method to do exhaustive search in practice, it would be important that this unitary is one that we can perform efficiently. That is indeed the case. Well, I guess you can think about it this way. There's some, I guess I should have written this out, but there's a unitary which acting on the 0 state creates S, okay? Like it could be that tensor product of Hadamard's or quantum Fourier transform. So you can think of this as the result of conjugating to projection onto 0 minus identity by that unitary that maps the state 0 to the state S. Conjugating meaning U times the operator 2 projection onto 0 minus 1 times U adjoint, okay? And so all I have to convince you of, since you already agree that there's an efficient unitary that prepares S acting on 0, is that the operator 2 projection onto 0 minus I is something we can do efficiently. So what is that guy? It's a controlled phase operation. So if I think of it acting on n qubits, and let's say I don't care about the overall minus sign, so you can think of it as something that flips the phase of the basis state 0 and leaves everything else alone. So that's like a controlled phase operation. It changes the phase triggered by the state being all zeros. And that is related just by changing basis, which you could do with a Hadamard, to a knot, which is controlled by all n qubits, where the knot on one of the qubits is triggered by all the other qubits being in the state 0. So that's like, I guess I called it lambda n-1 x back when we were talking about Toffoli gates. It's a controlled, blah, 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 not. And well, there's some discussion in the notes. I don't think I went into the details in class about how you can construct that out of Toffoli gates. We know how to construct Toffoli gates out of whatever our universal gate set is. And the number of Toffoli gates you need is linear in n, little n. So that would be logarithmic in capital N being the dimension of the Hilbert space. So I consider that to be efficient. And well, the whole point of that digression was just, although it doesn't matter for query complexity, we should know that this use of S is something that's not so hard to do with a quantum circuit. It doesn't require that many gates. Okay, so what happens when we first do UW and then do US? That's this Grover unitary, the Grover iteration. And so, well, we start out with the state S. So come down and look at my picture here. We start out with the state S. And then what UW does, remember, is it reflects in that hyperplane orthogonal to W. Now, these unitaries are going, if we start out with the state S, as we'll see, they're going to preserve the two-dimensional space spanned by S and the marked state W. So in order to understand what the unitary does, to see where the state goes, it's enough just to consider its action on that two-dimensional space, because the vector is never going to leave that two-dimensional space, the span of S and W. So it starts out being S. S makes a, has a small overlap with W. There's some vector in the hyperplane orthogonal to W with which it makes a, in which it's almost aligned, okay? So in other words, the angle theta is the angle between the S and this vector, which is orthogonal to W, which is the same thing as saying the overlap of S with W is the sine of theta. So the overlap of S and what I'm calling W perp, which is orthogonal to W, is cosine theta. So that's where we start out. And then we do this reflection in W perp, and that's going to move us down here to a state which it still makes an angle theta with the W perp axis, but now it's on, it's in the other quadrant. It flipped over to the other side of W perp. That was what the query did, the operation UW. Now we do US ourselves. The query, we have to go to the box. The US, we don't need the box. We just do it ourselves. And what that does is it reflects in the vector S. So let's look over here. Now, after we've done UW, we have a vector which makes an angle 2 theta with S, because originally it made an angle theta with W perp, but it got reflected in W perp. So now it's rotated by theta in the other direction away from W perp. The total angle between this state and S is 2 theta. Then it gets reflected in the axis S. So that means it winds up over here, rotated by 2 theta counterclockwise relative to S. Okay, so that's, I've indicated here, the result of applying the Grover iteration, first UW and US, on this initial state S. All right. So we rotated it further up towards W. We increased its overlap with W. We decreased its overlap with W perp. If we were to measure now in the computational basis, we will have increased the probability of finding the result W, and we will have decreased the probability of finding any other basis state, because W perp here is the overlap. Well, It's essentially the component of S, which is orthogonal to W, and that's just the uniform superposition of all the strings except for W. Okay, so we suppressed the W perp part and we enhanced the W part by doing this iteration once. So that's good. We're closer to having W than we were to start with, and we want to find that W when we finally measure at the end. So we do it again. So if we have any vector which is rotated counterclockwise, now I'm looking at the lower right here, which is rotated counterclockwise relative to S by an angle phi, we do the Grover iteration. So first of all, it gets reflected in the axis W perp. It's making the angle theta plus phi with W perp. It winds up rotated by theta plus phi from W perp in the clockwise direction from W perp here. And that's what the query does. And now we do U sub S, the unitary we apply ourselves. That reflects this vector in the axis S. It's now making an angle 2 theta plus phi with S. So it's going to wind up being rotated 2 theta plus phi counterclockwise away from S when we apply US. So that's what I indicated here. The initial state, psi, made an angle phi, rotated counterclockwise with respect to S. We do another Grover iteration, and that vector has been rotated counterclockwise further by another angle 2 theta. So every time the iteration consisting of the query to the black box and the unitary we do ourselves has the effect of rotating us counterclockwise in the plane spanned by S and W perp. And that means we're getting more and more overlap with the marked string, okay? And so what we want to do is keep continuing the Grover iteration until we have the maximal overlap of the vector with the marked state. Then we can measure in the computational basis and we'll find the string W with probability close to 1, okay? So we keep rotating, rotating, and rotating until the vector lines up with W, and that's when we measure. So how many times should we do the Grover iteration before we measure? Well, we started out with a state which was rotated counterclockwise by theta relative to W perp, and where we want to wind up is with a vector rotated by pi over 2 in this plane, counterclockwise from W perp, because that's W. We want W, so when we measure, we'll find that string. So every time we do an iteration, we increase the rotation angle by 2 theta. So we want the total number of iterations that we do, which I've called capital T, times 2 plus 1, which is the initial angle. All that times theta should be as close to pi over 2 as we can get. Okay, and theta is small. So each time we're rotating just a little bit. And when we stop, we'll choose theta, we'll choose T in such a way that the angle between the resulting vector after all those iterations and W is something of order 1 over square root of n, because we can, since we rotate 2 theta every time, we'll always be able to make that angle no larger than theta. If it's because successive orientations are only 2 theta apart. Once we get up to nearly vertical, one or the other orientation is going to have an overlap between our vector and W, which is no larger than theta. So with a small error, which is negligible if capital N is very large, we can, when we measure, find the marked string with probability very close to 1. The number of iterations that we need is to satisfy this condition. So T is going to be really big. The 1 doesn't matter much. So I can say the T should be chosen to be about pi over 4 divided by theta. And here it is, pi over 4 divided by, or pi over 4 theta. Theta is very close to 1 over the square root of n. So this is pi over 4 times the square root of n. The number of times that we query the box to find the string is essentially the square root of n, except for this numerical factor, which is whatever it is, 0.78, something like that. Okay, so it's really pretty remarkable. Classically, we're looking for a needle in a haystack, one out of capital N possible states, and we just have to check them one after another until we find the right one. Quantumly, though, we were able to do an exhaustive search over all of those possible strings. Even though there are capital N of them, we could do the exhaustive search in square root of n evaluations of the function. And the reason it works is because probabilities are the squares of amplitudes in quantum mechanics. If I were doing classical queries, and I did one query after another, after I've done little t queries, the probability that I found the needle in the haystack is increasing linearly with t, right? But quantumly, I can get it to increase quadratically because the amplitude is rotating by a constant angle every time. And the, so after I've rotated t times, the square of the amplitude is going to scale like t squared. Okay, so the probability of finding when I do little t iterations, the string that I'm looking for, is actually increasing like t squared instead of t, all because probabilities are squares of amplitudes. Then, so far I've discussed the case in which there's just one special solution, one marked string. Of course, it's possible there's more than one. If I'm trying to solve a problem in NP, there may be more than one solution. There may be more than one string that the verifier will accept. And let's suppose there's more than one, some number r. I don't know why I said greater than 2. I must have meant greater than 1, greater than or equal to. So suppose there are 2 or more solutions. Well, of course, if it's a small number of solutions compared to capital N, it's still a needle in a haystack. There are a few needles in the haystack, but it's going to be hard to find. There altogether are marked strings out of N. And in order to have some constant success probability for finding the marked string, classically, I'll have to query a number of times that scales like n over r, because the probability every time I make a query, if I make a random query of finding a marked state, will be r over capital N. But quantumly, we can speed things up. So the number of queries we need goes like the square root of n over r. It's essentially the same argument as before, except that now in that coherent superposition that we start with, the state S, the coherent superposition of all of the possible candidate solutions, now r of them are marked. So there's a marked state, which is normalized, which is 1 over the square root of r, the coherent superposition of all of those r marked strings, all the wi. And so the overlap of this marked state, and we'll be happy if we can get to this state, because then when we measure, we'll just be randomly sampling from the solution set. Okay, if we had the marked state and we measured in the computational basis, we get one of the wi's, one of the solutions, sampled uniformly, all those marked strings occurring with equal probability. So if I can reach that marked state, I'll be very happy. When I measure, I'll find a solution. Now the overlap of the marked state with our initial state is larger than before. Instead of going like 1 over the square root of n, it goes like the square root of r over n. So I can think of that as the sine of an angle. And theta is, assuming r is small compared to capital N, theta is essentially the square root of r over n. And the rest of the story is just the same, I'm going to do the queries, and I'm going to do the u sub s, which reflects in the axis s. The thing that's different is that the overlap of the marked state with s is given by a different angle than before. And so now, again, the number of queries that I'll need to reach the marked state with probability very close to 1 is still going to be pi over 4 theta, but now theta is a larger angle, square root of r over n instead of 1 over square root of n. So the number of queries that I need goes like the square root of n over r times that same numerical factor of pi over 4. So the point of this story is that even when there are multiple solutions, then you have you need a smaller number of queries to find one of the marked strings, one of the solutions with some specified success probability in the classical case. The number you need goes like n over r. The number of queries that you need quantumly again goes like the square root of the number of classical queries. It's n over r classically, and it's the square root of n over r quantumly. Now, it's sometimes said that Grover's algorithm is like a souffle. If you leave it in the oven too long, it starts to sink again. So you have to know when to measure. You have to measure at the right time. The probability of finding the marked string as a function of t goes up because you're rotating closer and closer to w. But if you just keep on rotating, then you start rotating away from w. Okay. And so if you were unlucky and you went too far and you queried for twice the number of queries that would give you the optimal chance of finding the marked state, you'd be back to having essentially 0 probability of finding it. So that would be bad. And we don't a priori know how many solutions there are. Well, let's hope there's at least one. But there could be some large number r. Capital N is huge. We'd be happy to find any one of them. But depending on how large r is, the state as we make additional queries is going to rotate at different rates, and we don't know what that rate is. So what do we do? Well, in choosing, we know if there is a solution at all, r is at least 1. And in that case, we know the number of queries that we need is pi over 4 square root of n. And the number of queries that we should choose if r is larger is going to be less than that. But what I can do is just sample uniformly from the possible numbers of queries ranging 1, 2, 3 up to, well, it'd be kind of silly to just do a few, but essentially sample uniformly from all possible numbers of queries up to capital T, which would be the optimal number of queries in the case where there's just one solution. And so then I'd be sampling from this sinusoid essentially. And because the average of the square of a sine function is 1/2, what that means is that averaged over the choice of the sampled number of queries, our probability of success is going to be 1/2. Okay. And so each time we have a pretty good chance of finding a marked state. If we find it, we can check that it's right because we just evaluate the function one time to be sure. So that's what we do. And if we don't find it the first time, we try again. And after a few trials, chances are we're going to find a solution. We're going to fail after m trials only with the probability, which is at least as small as 1/2 to the m. Now, so far I've been talking about the case where we just do completely blind exhaustive search. We really have no idea where to look for a solution. That's not always the case for NP hard problems. Sometimes we can make a guess, or we have information that indicates that some trial solutions have a better chance of panning out than others. And in that case too, we can achieve the quadratic speed up. Just as an example, suppose that of those capital N possible strings, there are actually a smaller number, capital M, which have a higher a priori probability of being solutions. And so I could try sampling just from those capital M instead of all capital N. And then in the classical case, the number of queries that I would need would scale linearly with M, but quantumly, I can still do it with square root of M queries. Here's what I have to do. The initial state that I want is going to be, let's say, if I don't have any reason to think any of these candidate solutions are more likely to succeed than others, the uniform superposition of all the candidates. So let's say there is some efficiently computable unitary. If I really want to do this in practice, I'd care whether it's sufficiently computable, which can prepare this state. So I could use that. And by prepare it, I mean acting on the basis vector 0, U gives this superposition. And so I can use that to prepare my initial state. I can also use it for the iteration. This is sort of what I was trying to say before. In the case of the Grover iteration, where all capital N strings are considered a priori equally likely, the unitary that appeared here was the unitary that mapped 0 to the uniform superposition of all capital N basis states. And then this conditional phase, which is triggered by the all 0 state, conjugated by that unitary, gives the unitary that we do ourselves as part of the Grover iteration. And in this case, if this unitary is something I can do efficiently, I'd use the same idea. I take this conditional phase gate triggered by the 0 string. I would conjugate it by U, and then I can do the analysis the same way we did it before, considering the angle between this state and the mark state, and then the way the angle is changed when we do the Grover iteration using this unitary ourselves as well as the query. The analysis goes through just the same way. And so the number of queries I'd need classically here is capital N, but quantumly I can make it order square root of N. And there you can generalize that a little bit more. But essentially, if you do some kind of search which is informed by the structure of the problem, if you can do it classically, then you can speed it up quantumly, quadratically, by using Grover's idea. Okay, so this is pretty cool. We've seen that quantumly we can achieve a quadratic speedup of exhaustive search compared to when we have only classical queries. And so it's natural to ask, is that the best we can do? Is having the number of queries go from the classical number, essentially n, to what can be achieved quantumly, square root of n, is that the optimal speedup? And the answer is yes, it is the optimal speedup. In other words, the answer to the question, the way I asked it here, is that we can't do better. No, too bad. So let's consider the case. And of course, we could talk about the case when there are many solutions, and it'd be a similar story. So let's go back to the hardest case, where there's just a single marked string, and we're trying to find it out of capital N possibilities. So our phase oracle is, this I think is where I went from W to omega. These are actually omegas now. Okay. Is going to flip the phase of the marked state, omega. It's not going to do anything to everything orthogonal to omega. And in the Grover algorithm, we used that U sub s in between queries. And now the question we want to ask is, what if I do some other unitary? In fact, I could pick a different unitary every time between queries. So I start out with some initial state, whatever it is. We had a particular initial state that we liked, but it could have been something else. And then we do any unitary in the world we want to on that state, and then we query. And then we do another unitary, which is ours to choose, and then we query, et cetera, et cetera, et cetera, until finally we do a unitary, and then a query, the final unitary, and then a query. I could have put another query at the end, but that would only affect the basis that I have to measure in the end, so I didn't bother with that last query. But anyway, this is the general situation where I have capital T queries and general unitaries between the queries and some general initial state that we started with, okay? Now, the state that we wind up with, if we run that procedure, is going to depend on the marked state, because all of the queries depend on that state omega. And so there are really n possible states that we can generate through our procedure. Once we fix the unitaries that we apply, the capital N possible states correspond to the n possible marked states, the n possible ways in which the oracle could act when we do a query. Now, the unitaries that we do don't make it easier to tell the different marked states apart. So what we would like is for these n vectors, once we're done, the n possible vectors we could get for the capital N possible choices for what the queries do, is we want them to be as distinguishable as possible so that we can measure and find out as much information as we can about which omega it really was, okay? So what we want is for the vectors, as we apply more and more queries, to splay out from one another, to separate, so they're easier and easier to distinguish from one another. But that splaying of the vectors, which makes them easier to distinguish, that's not something that happens when we do our unitaries. When we do our unitaries, U1, U2, et cetera, that just rotates all of those n vectors together and doesn't change their relative orientation at all. It's only the queries that can do that. And in the end, if, when we're done, we really want to be able to identify the marked string with a very small probability of error, we want them to be almost perfectly distinguishable at that point. So we want these capital N possible vectors to be very close to mutually orthogonal. And then when we measure in the right basis, the computational basis, if we played our cards right, we'll be able to unambiguously identify which omega it was, because those capital N vectors can be perfectly distinguished from one another by the measurement. So what I want to do is I want to keep track of how those vectors splay apart as we do one query after another after another. And what I want to see is that we're going to need lots and lots of queries to make all capital N possibilities distinguishable from one another. And that's how we'll obtain a lower bound on the number of queries that are needed to find the marked state with low failure probability. So to keep track of that splaying, it'll be convenient to, instead of looking at how vectors for different values of W separate from one another, I'll look at how the vectors for a given W deviate from some fixed reference vector. Well, it's fixed at least in the sense that it doesn't depend on W, although it will depend on the number of queries. And that'll be a convenient way to analyze how far apart all of the UW of T's are getting from one another as we increase the number of queries, okay? That's our strategy. The reference state that we're going to use is going to be a state like this, except we leave out all the oracle calls. One way people sometimes say it is we replace the oracle by an empty oracle that doesn't do anything. It just applies the identity. We could just as well say we don't do the queries. So we'll do our unitaries, U1, U2, U3, etc., but with no queries in between. And that will define for each value of little t a reference state, which I'm going to call phi of t. And what I want to keep track of is how far apart is psi sub w of t, what the state has become when we're querying with a box that marks the state omega, or w, whatever it is I'm calling it. And so after little t queries, psi omega is going to deviate from the reference state phi of t by some amount, which is e sub w of t. So phi is a normalized vector, psi sub omega is a normalized vector, e sub omega is not. It's just the difference between the two, and I had to call it something. Okay. So just repeating some of the things I just said, psi omega of t is the result of doing, here now I have little t, because I want to see as t increases how this deviation is going to be affected. So this is after I've done little t queries with unitaries of my choice, U1, U2, etc., in between the queries. And I'm going to write this vector as my reference vector, phi of t, which is obtained by the same sequence of unitaries that I chose, but without any of the queries to the box. I'm going to write it as phi of t plus the deviation. Okay. And now I want to look at how that deviation is affected when I do one more query. Well, I do one more query after doing one more unitary of my choice, the t plus 1 unitary, u sub t plus 1, and then I do the query unitary. So after I've done one more query, I have the state psi omega of t plus 1. That's obtained by acting on psi of t with u t plus 1 and u omega. Psi of t is equal to phi of t plus deviation of t. So I have u omega u t plus 1 acting on phi, the reference vector, plus u omega u t plus 1 acting on the deviation. And that's what psi sub w is after one more query. But I want to compare psi sub w with the new reference state because I've added 1 to the time. The reference state is depends on the number of unitaries that I've applied. When I apply u t plus 1, the reference state becomes phi of t plus 1. So I want to keep track of the difference between the reference state and the vector that we got from the queries after one more time step. So for that purpose, it'll be convenient to write the query unitary as the identity plus its deviation from the identity. It's I plus u sub w minus 1. So when I do that, I have this term which is u omega ut plus 1 acting on phi of t. But from the identity piece here, that's going to just give me u of t plus 1 acting on phi of t. That's phi of t plus 1. Okay, so that's good. So now I've written psi sub omega t plus 1 as the reference state of t plus 1 plus some other stuff. That other stuff is the new deviation. The contributions to the new deviation are, first of all, the rest of the unitary, u sub omega minus 1, acting on the deviation that I get from applying ut plus 1 to phi of t. So that's this guy. But then I also have to consider u omega ut plus 1 acting on the deviation from the previous step. So now the new deviation is going to be the sum of this term and this term. So what I'm calling e sub omega t plus 1, the deviation from the reference vector after t plus 1 queries, is going to be given by u omega minus identity acting on the reference state at t plus 1 plus u omega ut plus 1 acting on the deviation at the previous step. Okay, so Now I'm just going to use the triangle inequality to get a bound on how much that deviation grew in that last query. I'm going to say that the deviation after t+1 steps by the triangle inequality is less than or equal, and I'm using the operator norm to keep track of its size, the sup norm, is less than or equal to the deviation at step t. Well, that's just the sup norm. Well, sorry, not sup norm, because these are states. I just mean the norm of the state, you know. Okay. You know what the norm of a state is. It's not an operator. Now, use of omega times u t+1, that's just a unitary, a product of two unitaries. So that doesn't change the norm of this vector. So in my triangle inequality, this just becomes the norm of the vector e sub omega of t. And then I also have this term, which is the norm of the vector resulting from u omega minus identity acting on phi of t+1. Okay. Now at this point, let's remember what the queries do. What unitary u omega is. It's this guy. It's identity minus 2 projection onto omega. It changes the phase of omega. It doesn't do anything to the states orthogonal to omega. But here I have u omega minus identity, so that's just, except for this minus sign, twice the projection onto omega. So what I have here for my bound on the difference between the deviation after t+1 steps and the deviation at t steps is 2 times the absolute value of this inner product of omega with phi t+1. That's because I just plugged in what u omega is into this expression, the second term in the triangle inequality. All right, so that deviation is going to grow with time as I do one query after another. I have a bound on how much it grows in each step for each query, and then to get a bound on how large it has grown after capital T queries, I just have to sum up these increments over capital T steps. So it's going to be the overlap of the marked state with the reference state at time little t, absolute value, times a factor of 2, summed over all values of little t. The first query, the second query, the third query, and so on. So that's my bound on the deviation after capital T queries in the case where the marked state is omega. Now I'd like to write this in a different way using the Cauchy-Schwarz inequality. Here I have the sum of some absolute values of complex numbers. What Cauchy-Schwarz says is that the sum over little t of the absolute value of c sub t can be written as less than or equal to the square root of capital T, the number of terms, times the norm of the vector whose components are absolute value of ct. In other words, the sum over little t of c sub t squared, square root of that quantity. You may be familiar with Cauchy-Schwarz as saying that the absolute value of an inner product is less than or equal to the product of the norms of the two vectors in the inner product. This is just a special case of that. You can think of the two vectors in that version of the Cauchy-Schwarz inequality as being the vector with capital T components, where the components are the absolute value of c sub t's, and the other vector is the vector with capital T components where every component is 1. So the expression on the left here is just the inner product of those two vectors. The norm of the vector, all of whose components are 1 when there are capital T components, that's just the square root of capital T. It's the square root of the sum of 1 plus 1 plus 1 plus 1, etc., t times. And then the norm of the vector whose components are capital absolute value of c sub t, that's just this expression, the sum of those components squared, square root of the whole thing. So that's just Cauchy-Schwarz. So what it tells me is the norm squared of this deviation. And just to remind you what it is, that means the norm squared of the difference between the reference state after capital T states and the state that we get when we include the query, psi sub omega of capital T. We had that it could be bounded by the sum. And now I've squared it here. So what I can do is square the right-hand side of the Cauchy-Schwarz inequality here. I had this factor of 2 that gets squared to become 4. I had this square root of t that gets squared to become t. And then what's left is the sum of the squares of these overlaps, the sum of this absolute value squared of the inner product of omega with phi of t, okay? Summed over little t from 1 to capital T. So now we have an upper bound on the deviation at capital T steps, the deviation of the case where we include the queries from the case in which we don't include the queries. Now, that applies for all possible choices of the marked state. Omega could be any one of capital N possible basis vectors, which is marked. And so that's here I just rewrote what we had on the previous slide. So now what I'm going to do is I'm going to sum those deviations over all the possible marked states. So I'm going to sum the possible marked strings from 0 to capital N minus 1, for each one of which I know that this deviation squared can be bounded as shown here. And but now I'm going to reverse the order because why not? They're finite sums between the sum over little t and the sum over omega. And the nice thing about that is that the sum over omega of absolute value squared of inner product of omega with phi of t, that's just equal to 1, okay? Because it's just the sum of all the components of phi of t along an orthonormal basis squared. And it's a normalized vector. Phi of t is a normalized vector. So that sum is just going to give me 1. And so then I've just got 1 summed from little t equals 1 to capital T. That's just 1 occurring capital T times. So that sum is just capital T times 4t. So this is 4t squared. We have 4t squared as an upper bound on the sum of the deviation squared summed over all the possible marked states. Okay. Now suppose it's true that with success probability extremely close to 1, that we can identify the marked state perfectly. That means that the different vectors corresponding to different marked states have to be mutually orthogonal. Right? Only in that case would I be able to essentially perfectly distinguish them. Now, that means that in the case where the success probability is essentially 1, the psi omega of capital T's should all be elements of an orthonormal basis. Now, for any orthonormal basis and any fixed vector, I can consider the sum over the basis elements, the difference between basis element and fixed vector, norm squared. And when I evaluate that, well, the norm squared, that's just the inner product of this guy with itself. And so we get the inner product of I with I and of phi with phi, that gives me 2. But then we have minus inner product of I with phi minus inner product of phi with I. That's just going to be minus 2, the real part of the inner product. So here I have 2 appearing capital N times. So that just gives me 2n. And then I can get a bound on that by asking what's the largest that these real parts can be. Well, they can't be larger than the modulus of the inner product. That would be the case in which the inner product actually is real and positive. And so I can write this as 2n minus this sum times 2 of I equals 1 to capital N minus 1 of absolute value of inner product of phi with I. But that's just the kind of sum that we bounded using Cauchy-Schwarz on the previous slide. It's bounded by the square root of the number of terms, by the square root of n, if phi is a normalized vector. And so what we have is that this is greater than or equal to 2n minus 2 square root of n. So n is really, really big. So the square root of n is really small compared to the n. I can write this as 2n times 1 minus some little correction. I wrote little o of n, which just means that as capital N gets large, this becomes as small as you please. So what this is telling us is that we know that 4t squared is greater than or equal to this sum. We know that if the psi omega of capital T's are perfectly distinguishable, then this sum is greater than or equal to 2 capital N times some small correction, which I'm not going to worry about. So that tells us something about the number of queries. The number of queries that we needed to make these states distinguishable had to be, let's just divide by 4 and take the square root, had to be at least the square root of n over 2, about 0.707 times the square root of n. What we found using Grover's algorithm is that we can find the marked state by choosing those unitaries to be the right unitaries to do the Grover iteration, capital T times. Then with Grover's algorithm, the number of queries used is pi over 4 times the square root of n, just a little bit bigger, 0.785 times the square root of n. And that's pretty close. So we have an upper bound on the number of queries because we know we can get probability essentially 1 for finding the marked state using Grover with 0.785 square root of n queries. But what we've seen is that we needed to have nearly that many. We needed to have at least 0.707 square root of n. Now, actually, if you tighten this argument up and you put in a little more detail, you can close the gap between the 785 and the 707, and it's really the case that we need pi over 4 times square root of n queries to get an arbitrarily small failure probability when we measure to identify the marked string. Now, this is all in the case in which I demanded that we have a success probability which is essentially 1. Of course, we might be willing to settle for some success probability less than 1. What if for any choice of the marked string, we say it'll be okay if we identify it with a success probability of at least 1 minus epsilon? So we're allowed to fail with probability epsilon, but no worse than epsilon for any choice of the marked string. Well, then we can change the story a little bit. That when we make our measurements at the end in the appropriate basis, it's okay for the states to deviate away from the orthonormal basis, which is labeled by the different marked states. So it would be all right if, after we've rotated the basis to line up the vectors as best we can with the computational basis elements corresponding to marked states, that in the case where omega is the actual marked string, when we're done with all our queries, we have omega times some coefficient a sub omega and something orthogonal to omega with coefficient b sub omega, such that when we measure, the orthogonal case occurs with probability no larger than epsilon, which means that the amplitude for the orthogonal piece shouldn't be larger than the square root of epsilon. Okay. And so when we take the overlap of psi omega of t with phi, the reference state, we get a contribution which is a omega, but I'm just going to bound that by 1 times the overlap of phi with omega, the inner product of phi with omega. But then there's this correction, which can't be larger than the square root of epsilon, coming from the inner product of phi with the orthogonal part of psi omega. Okay. And now we just run through the argument again. We know that for t squared is greater than or equal to this quantity. That's true no matter how many queries we have. And but then I use this result to bound this, that I'm going to, well, I can just write this out like I did before as 2n minus 2 times, well, it's actually a bound, minus the absolute values of the inner products of the psi omegas with phi's. And so I get the 2n from this term and the minus 2 square root of n, which we got from this part of this inner product. But then there's an additional piece coming from the error, coming from the component which is perpendicular to omega, which can be as large as square root of epsilon in each term, and they're all together n terms. Well, actually 2 square root of epsilon in each term. And so I get this minus 2n square root of epsilon. Well, as before, the square root of n is negligible compared to capital N when n is really big. But the epsilon also comes multiplied by capital N. So what we conclude for the number of queries, if the probability of success is at least 1 minus epsilon for each possible choice in the marked state, is square root of n over 2, what we had before, negligible correction when n is very big, but now 1 minus square root of epsilon. And because this is a bound on t squared, I have the square root of 1 minus the square root of epsilon. So for some order 1 epsilon, it's not much different than before. The coefficient of square root of n changes a little, but the number of queries that we need will still scale like the square root of the dimension of the Hilbert space if we're looking for one marked state. So the conclusion is that even when we allow for some probability of failure, as long as the probability of failure is bounded for any choice of the marked string, the number of queries that we'll need to identify the marked string is still going to go like the square root of n. We can't do better than that. So what's the broader lesson from that? Well, you might take it as suggestive evidence that NP is not contained in MQP, in BQP, that we can't solve NP complete problems with quantum computers. Why do I say that? Well, at least we can't, by just using the power of quantum superposition to speed up exhaustive search, do better than a quadratic speed up. We can't get an exponential speed up by doing exhaustive search on a quantum computer to try to solve a problem in NP. That's just not enough. If we're going to do better, then somehow we have to take advantage of the structure of the problem so we can do something better than just testing all the possible solutions or testing from some very large pool of possible solutions. We would have to take some NP complete problem, make use of its structure to speed up the solution quantumly in some more dramatic way. But nobody really knows of any such structure for NP complete problems that would allow us to speed them up dramatically, classically or quantumly. If there is such structure, well, we just haven't gotten a glimpse of it so far. We don't know how to improve on exhaustive search for some hard instances of NP complete problems. And if we can't do better than that, then quantumly, we're not going to do better than a quadratic speed up. Because when it comes to speeding up exhaustive search, the quadratic speed up is the best we can do. Okay, so that's the story of exhaustive search on quantum computers. And polynomial speedups, quadratic speedups are nice. Maybe they'll be important someday. I guess one way of saying it might be this. Let's say there's some maximum instance size, maximum input size, rather, that we can handle with a classical computer in solving some search problem. Then with a quantum computer, assuming the quantum and classical computers have about the same clock speed, we'd be able to handle inputs which are twice as big. right? Because, you know, the square root of 2 to the n is 2 to the n minus 1. So yeah, I guess that's right. So that's okay. You know, if we had to stop at 1,000 bit inputs for a classical computer, maybe we go up to 2,000 bit inputs for a quantum computer, and that's better, but it's not sensationally better. And you know, the truth is that for the foreseeable future, there's going to be overhead with quantum computing because of the need to do error correction. If we're going to run circuits which are of reasonable size for solving really hard problems, we're going to have to use quantum error correcting codes, and that means extra qubits to have sufficient redundancy. Now, formally, the theorem that one can prove about quantum error correction is that once the error rate is below a certain threshold of accuracy, the overhead cost is just polylog. And so in principle, if you have a quadratic speed up, but you have to pay a polylog price to have sufficient redundancy to run your algorithm reliably on a quantum computer, you're still going to win. But that might only kick in asymptotically for very, very large inputs. And so I'm not terribly optimistic about, say, sometime in the 21st century. Well, who knows? That's too far off. I shouldn't say that. But at least, let's say in my lifetime, and I, as you know, am still a very young man, I don't expect to see a lot of practical impact of the quadratic speed up for exhaustive search. Sad to say, but it certainly is a cool idea, and it's there's a lot of beautiful theory about other types of polynomial speedups, which unfortunately we're not going to take the time to discuss. What I would like to discuss is using quantum computers for quantum problems, because based on our current understanding, that's where we have the best hope that quantum computers will have a big impact on the world. And so that's what we'll start discussing in the next lecture. But so I guess that's it for now. And hope to see you next time. In the meanwhile, take good care of yourself. Be well. I'll see you soon.